Rates of reactions. Oh, we have lovely red today. Rates of chemical reactions. That's what we'll call this little lesson. Now, what we mean by rate, of course, the rate of something is how fast it goes, right? So that's what rate means. It's a comparison with time, how fast it goes. Okay, when you start studying physics, you compare lots of things to time, and we study a lot of rates, how fast things go. Rates are very important. In fact, when you study calculus in grade 12, that's a whole mathematics that's designed to help us study rates of things and how they happen, which is pretty cool. Okay, so how fast do reactions go? Well, let's think about this for a minute. Let's say we write a reaction. Okay, let's take a simple reaction. I'll go back to black here. NaCl, sodium chloride, and let's say it's going to react with magnesium phosphide. Okay, all right. And if I told you this was a double displacement reaction, you can write the products and balance it, couldn't you? So I'm going to pause and let you do that. All right, so we have sodium is going to go with fluorine this time, so NaF. And then magnesium chloride. And then, of course, we have to balance it. So hopefully you wrote it like that. And then when you balance it, you have to put a 2 right here and right here, I think. And that will make everything work out. So practice, practice, practice. That's what chemistry is. Okay, so now let's talk about this. So this is all a bunch of words on paper, but let's imagine what we're actually talking about. We're talking about some stuff that's going to be mixed with some other stuff, and then it's going to produce this other stuff, right? Now, let's take pictures of this. Let's take a big cup, and let's put some water in it. Typically, when we do these reactions, water makes them incredibly more easy. And we're going to explain why that works in our next video. But for today, we're just going to sort of look at these cups of water. And we're going to imagine that all of this mixing and matching is happening inside the cups. Okay? So, let's just think about it. If we put some sodium chloride in the water, then there we can put little dots. There's the sodium chloride floating in the water. Right? And then over here, we have this magnesium fluoride floating in the water. Like, you know what I'll do? Actually, I'll use a different color for that. Not that it really matters, but just, okay? Now, when we're done, they've all traded partners, right? And now we have over here sodium fluoride, which is a different partner, and over here magnesium chloride instead of magnesium fluoride. But let's think about what happens right here when they're all mixed together. Okay? So what's actually happening in this, when you mix them in the water, right? You have your sodium chloride floating around, and your magnesium fluoride floating around. And whenever they sort of bump into each other, that's when they can trade partners. So slowly, we start getting some of the sodium fluoride beginning to form every time a red and a black dot sort of bump, right? It's actually a little more complicated than that, but we'll explain that later. And a few purple dots starting to form. So it's all kind of happening in there, right? Now, does it happen really fast? Like, boom, and all of a sudden it's all blue and purple? Or does it happen really slow, a little bit at a time? So one little purple forms, and then one little blue forms, and it takes about 10 minutes for it to happen. That's what we mean by the rate, right? So one of the things that can speed this up is, if we remember grade 9, there was something we learned called the particle theory of matter, which is sort of a shortcut theory that we learned in grade 9, but it tells us something about these particles, these little things. They're always jiggling around, right? They're always moving and jiggling. So really, what we could do is we could imagine, little jiggle marks around each one. They're just kind of like shake, shake, jiggle, jiggle, shake, shake. And of course, if you jiggle and shake a little bit, then you're only moving a little bit. But if you jiggle and shake a lot, chances are you might bump into somebody else, right? So the more jiggling and shaking there is, the greater the chance you'll bump into somebody else and trade partners and make the reaction happen. What makes these particles jiggle? Heat. Heat is the energy that makes particles jiggle. So if you add heat to a reaction, or if you add heat to this water, they'll jiggle faster, bump into each other quicker, and the reaction will happen much faster than it would if it was colder. Because when it's cold, they're just jiggling a little bit. So our first factor that affects how fast things go is heat. Heat, which is a form of energy, right, increases the rate of a reaction, makes it faster. So we warm things up, they goes faster. Right now it's fall, right, where we are. And in the fall, the temperature starts to drop. Now think about the chemical reactions inside of grass growing outside. In order to grow, all these chemical reactions have to happen inside the grass, right? And so in the summer when it's hot, those chemical reactions can happen more quickly because it's warmer, which means the grass will grow faster in July and August. We have to go outside and cut the grass every 3 or 4 days. But now as we get into September and almost October, it's getting colder outside. So the grass is still growing, but it grows slower. Now you only have to cut it every week and a half or so, right? Have you noticed that? That's because the colder air means that the chemical reactions of life inside the grass are slowing down. When we do chemistry, we often will use a burner or a hot plate or something to heat things up to make reactions happen more quickly. So remember, hotter means faster, colder means slower. That's the first thing. And it has to do with the fact that hot makes the molecules and the compound things, the ions, it makes them jiggle more vigorously and increases the chances that they'll bump into each other. Pretty straightforward. Okay, now let's look at our cup again. Okay? If I put just a couple of each in there, there's my original 2 colors were black and red, I think, right? That was my sodium chloride and magnesium fluoride right here. If I just put a few little blobs of each, a few little compounds in there, how long is it going to take for them to bump into each other? It's going to take a long time, right? They're going to jiggle around in the water, randomly moving around, jiggle, 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 jiggle. Eventually they might bump, and if they do, oh, they bumped, and then, look, they traded partners, and we get a little bit of this. But this is going to take forever. It would be faster if I put lots of the sodium chloride in, and I put lots of the magnesium fluoride in. Now when they jiggle around, because it's a crowded room, right, there's a much better chance they're going to bump into each other. So by putting more of something into the solution, we can increase the chance of the reaction. It kind of makes sense, right? If you want 2 people, or if you want to get people to pair off in partners, and you have this gigantic football field and only 2 people running around on it, it's going to take forever for them to bump into each other. But if you put a crowd of 300 people, they're going to bump like crazy. So what do we call it when we put more of something into a solution? Does anybody remember that from elementary school? There's a word we use. It's called concentration. Okay? And we use words like solute and solvent to describe. The water is the solvent, and the stuff we're putting in, the sodium chloride, the magnesium fluoride, those are the solutes, right? And if you put lots in, you have a high concentration. So a high concentration means you have lots. But a low concentration means you have much less, or a little bit. And low concentrations because there's only a little bit, will go slower. Reactions will go slow. High concentration reaction will make the reaction go faster. So we can write that increasing the concentration, which basically means adding more stuff. Increasing the concentration speeds up the reaction or increases the rate. And the opposite would be true. I'm not going to write the opposite. Obviously, if you decrease the concentration, it would slow down the reaction. But that's sort of implied by the statement here. So that's another way to get reactions to go faster or slower. Increase or decrease the concentration. But remember, the increase means speed up and the decrease means slow down. Okay. Now lastly, or not lastly, there's two more to look at. Let's imagine a different picture now. Okay? Let's imagine that I have a block. And I want to sort of bump it into another block. Well, when you bump the blocks together, the only place they can touch is right here, in between, right? And if I drew those as sort of 3D-ish, maybe we could see that they would only be touching on that side, that part of the surface. But there's a whole lot of block surface that isn't touching, right? So we could calculate the area of the surface of the block, right? Length times width or whatever. That could tell us the area. And we would say that, this face of this black block has an area and it's touching the face on the other side of this blue block. That would be what we would call the surface area of touching, the surface area. And of course, touching means that you can react. You can trade partners if you get things to touch, right? So to speak. But is there a way where we could get more of the black box to touch more of the blue box? Is there a way we could make them touch more? Well, there actually is. Because what we can do is we can chop them up into little blocks. And when you chop them up into little blocks, they can, I'll draw them touching. They can touch each other like this, right? But now they can touch on different sides. So you can have a black touching here. In other words, by chopping them up, pieces of the blue block can float over and touch on the top or on the sides. In other words, we can get them to touch in more places. Does that make sense? Because if they're chopped up, they can all sort of mix around. So a piece right here, let's say we took a little block over here. Right now, he can't touch anyone. He's out of the picture. But if you break him off and let him run around, he could float over here and touch on this side, and now he can also react. So what we do when we chop something up is we increase, okay? If we cut something up, cutting into smaller pieces increases the surface area that can touch. I can touch other things. So what this means is we make more surface available, right? And another way to look at making it, that we could think of it this way. If I take this block, all right, I could calculate its surface by doing length times width. I could calculate the top and times 2 for the bottom, and then this, the front and the back, and then this side and the other side. And that would be all the sides, right? There'd be 2, 4, 6 sides that I would have to count up. But think about the inside of the block. It's touching nothing. But if I cut it in half, let's cut this block in half. Look what happens when we open up the halves. Here's one half, and here's the other half. There's a new surface here. This part was inside the block before, and of course you can't see it, but it's on the other side of there too. Two new surfaces have formed that weren't there before. They were not counted when we did the surface in the full black block. They were inside, but now we've opened the block up. If you add up the old surfaces, this one, and this, they all still add up to the same as the originals. So we added more surface area by breaking it open. We've got the inside. And the more you chop it, the more inside you expose. And that means increased surface area, which means faster reactions, because there's more places for the things to actually react or touch or interact with each other. So increased surface area. And the way you do that is by, let's put smaller pieces here. That's how you do it. You make the pieces smaller. Increases the rate, makes it go faster. So the most common way to increase surface area is to grind something up into a powder, right? Typically, the things that we use in chemistry are in the form of a powder, a ground up powder instead of a big solid chunk, because the powder has immense surface area. All of the inner pieces of a large block can be exposed if you grind it into a powder. And so powders tend to have lots of surface area, so they will react faster than putting two big blocks of something beside each other. Make sense? So increasing the surface area by grinding up or cutting up into smaller pieces. Then the last thing is something called a catalyst. So a catalyst is an interesting thing in chemistry. It's a substance that helps a reaction happen but doesn't actually get involved. Right? So if we have, let's say, a substance here, we'll call it A, and we want to react with substance B, well, if we just put them together, not much happens, blah, 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 blah. It's very slow. It doesn't seem to be doing much, not exciting. But we discovered that if we take another substance, C, right? So if we take A plus B, right? And we put this other thing just sort of around it, call it C, what'll happen is all of a sudden, woo, they'll all go crazy and A, B will form like nuts. The reaction will happen. But notice there's no C over here. The C isn't involved. He just happens to be there. Right? The C happens to be there, and it somehow makes, it's like if you had two friends that you wanted to set up on a date. Well, if you just waited for them to meet, they may be too shy, they don't know each other, they might never meet. But if you went with them for the first time just to introduce them and say, hi, here's my friends, you could help them meet faster. And then you could step out of the picture. You don't want to be involved, you just want them to meet, right? And once they meet, you back away, and now maybe they'll form a friendship or a relationship of some kind. So you were the catalyst. Here, C is the catalyst. It's a thing that somehow helps two other things get together. How it does that is quite complicated. But I can tell you that one of the ways in which catalysts can work is by sort of providing specialized shapes. In biology, we use catalysts for everything. Biology, living things like you and me, we are dependent on catalysts to make all of our chemical reactions work. So a catalyst is called, it's called a catalyst in chemistry. In biology, we give it a special name, and I'm sure you've heard of this. It's called an enzyme. An enzyme is a kind of protein molecule, and it is, one of its functions is that it acts like a catalyst to make other things happen. But it doesn't enter into the reaction, it's just around. And essentially what enzymes do is they're big bulky molecules, and they have like bumps in them. And so these bumps are perfect places for molecules to sort of lock in place like this. And when they lock in place in the bumps, they're being held together. It makes it much easier for them to join up, you see? So that's kind of a very basic way of how a catalyst might work. It might form sort of a platform on which other molecules can sort of line up, which puts them in a nice, easy position to form a reaction, to go together and do something. So that's what we mean by a catalyst. So basically, a catalyst increases the rate of a reaction. If you don't have a catalyst, so this is not you can't have a little bit of catalyst or it's basically you have the catalyst or you don't, right? It's there or it's not. Catalyst increases the rate of the reaction. So it's like a helper molecule that can help bring the other two together. And these are the four things that can make reactions go faster. Or in their opposites, they can make them go slower. And that's all we really wanted to learn about today, was just these things and how they influence the speed of a reaction. So to sum them all up very quickly, there is, first of all, there is the amount of heat, because heat jiggles them around more and they bump into each other more and they go faster. They can react faster. Concentration, the more they have, the better the chance they'll bump into each other. So increasing the concentration by adding more causes the reaction to go faster. Surface area, by cutting them up or grinding them up, we expose more of their inside surface that's not available when they're in a big block. That means there's more places for them to rub together, so that means that they can go faster. And lastly, if you have sometimes this special molecule that can help the two things get in the right position, or perhaps maybe just get in the right sort of, the right kind of energy level. It's all about energy, right? And that's what they do. So if the catalyst is around, it can make everything go fast. And if it's not around, everything goes slow or not at all. And that's it. Good.